Hi, today we'll be starting a chapter for IGCSE Physics titled Forces and Energy. So we'll be talking about things like what exactly is work? What's the force you need to push something over distance so you can create work? What is energy? What types of energy do we have? What is the law of conservation of energy? What's the efficiency? What's the power? How we produce energy? What's our resources? What is renewable and non-renewable energy, and how we can harness energy from the sun? So, generally speaking, let's go to the basics first. We do work a lot of times in our lives. For example, grabbing a cup of water, moving our hands, walking from this side to the other side of the room. We're using work. What exactly is work? You can use the annotate button here. What exactly do you think work is? Anyone can answer.
The energy needed to do something.
More precisely, the energy done when a force moves something. So, for example, I have a box right here. Let's say I apply 5 newtons of force to it. After this block has traveled, say, 2 meters, how much work have I done in terms of joule?
10 joules.
All right, very good. So what exactly is a joule? We know that a joule, which is a standard unit, is work done when 1 force of Newton moves an object 1 meter in the direction of the force. This is very important to state that it moves in the direction of the force, because if you have work done perpendicular to the distant direction of the force, you actually get no work done. This follows force times distance times cosine theta, but we will cover that in a later level. So things that have energy, they can be used to do work. For example, if I move a ball or if I throw a ball, it has energy because it's moving. There are materials too, where materials are always in motion. So let's say we have iron here. The solid, if the atoms are vibrating, you heat up the solid, they get more internal energy. That's why they move more quickly. So material contains more energy when it's hotter compared to when it's colder, because it stores more thermal energy. So we have a few types of energy here. Now, before I open this up, what types of energy can you guys name? I think each of you can name at least 2 to 3. You can write in the text here. What types of energy are there? I'll start with the first example, a very basic one. Kinetic energy. So kinetic energy is the energy stored in a moving object. Now, who can name other types of energy? All right, thermal energy, chemical energy, gravitational potential energy, internal energy, nuclear energy. Yep, that's good. So, what is each one of them? First up, kinetic energy is an energy when an object is moving. So, for example, if a ball is moving, it has kinetic energy. But potential energy is energy which is stored. So there are a few types of potential energy right here. Let's say a ball is about to fall off a cliff. It has gravitational potential energy. From this example here, the stone held on the air can also do work because It's gravitational potential energy. Or how about springs? For example, if you compress a spring before it releases, it also contains elastic potential energy. Or what about when we eat food? After eating our food and our intestines processing our food, it turns into chemical potential energy. So chemical potential energy is important because we'll use this food as fuel. For example, if I want to make a run to the kitchen, I'll need to use chemical potential energy. It's like a fuel. It can be in batteries, it can be in cars, it can be in humans too. Electrical potential energy is much rarer, but nuclear potential energy is more common. In nuclear reactors, they have to use materials like uranium, where once you split it up, it breaks down into two smaller nucleons, atoms, sorry, with a release of a lot of energy. Now, how this works is also pretty advanced, but we actually follow a mass and an energy conservation rule here. We also have a few other things like thermal energy, which also is like a transfer of energy. For example, if a cup of hot water, if a cup of cold water, when you mix it in the container, the hot water will transfer the energy, cold one. You also have radiation energy, for example, from the sun, or let's say when you're cooking, there's a lot of heat generated. Sometimes you don't need to touch it to feel the heat, but because the heat can really reach you from there. But usually, we can feel the heat from the sun due to the radiation. They carry energy too. So let's work on an exercise here. Shall each of you take turns on doing 1, 2, 3, 4, 5? So let's start with Alvin. How much work is done when a force of 12 Newton moves an object a distance of 5 meters? What formula would you use for this?
W equal to FP.
Yep.
So because force times distance, so 12 times 5 meter means it's 16 Newton meter. 16 Newton meter.
What's a better unit for Newton meters? What's a more appropriate unit that we'll use here? Because Newton
Volt.
meters, joule,
Joule. Okay.
not volt. Newton meter is usually used for moments of force. Let's try. Xiaomi, maybe you want to try the second one. If I use 40 newtons of force to lift a bag, I do 20 joules of work. How far do you lift it? Let's rephrase it because when you lift the bag, you might have gravitational potential energy. Say I have an object. I use 40 newtons of force. I move a certain distance. In the end, I have done 20 joules of work. Try rearranging the equation. How far have I moved this block?
Distance equals to work over force then, is it?
Yep, distance equal to work over force. So what values will you be substituting here?
20 joules over 40 Newton.
So what will you get?
The distance would be 0.5 meter.
0.5 meter. Right. Now, question 3 is pretty simple, so I don't think I need any one of you to attempt this question. Since it's common knowledge that kilo will be 1,000, mega will be 1,000,000. Let's try a more interesting one. Yinzi, maybe you want to try the fourth question. So I'll just scroll up to the values there. How many fully charged car batteries are needed to store an amount of energy equal to 1 liter of petrol? I'm just going to underline. how many of these fully charged batteries do I need so that it is equivalent to 1 liter of petrol?
35 million joules divided by 2 million joules.
This is a little trick.
17.5.
Yes, but once you get the answer, be careful. It is not 17.5. Why? Because you cannot get half a fully charged car battery, remember?
Oh, 18.
Which is why we need 18. So even though it exceeds more than this amount, 18 is what we need because we cannot have half a fully charged car battery. I'll
Okay.
appreciate if once I ask the questions, you can actually do the annotations on the makes it a little simpler to view.
Okay.
Let's go ahead to energy, conservation of energy. For example, you have a rock, you throw it upwards. When it's moving, there's kinetic energy. Then, once it's its highest point, it doesn't have any speed anymore, so it's stationary for a very short while. So it has some gravitational potential energy here. And once it falls down, it's kinetic energy. And once it hit the wall, it will be transferred to thermal plus sound, because usually when you throw something and it lands on the table, it also produces some sound energy. For example, if I throw this pen right now, energy is also dissipated as sound. So who can tell me what's the law of conservation of energy? What do we usually say about conserving energy? Try a guess for it.
We need to know potential energy before, no, kinetic energy before equals to gravitational potential energy after.
Yeah, but in general, what is the law in general that we have to follow? Not just kinetic, not just gravitational.
The loss in energy equals to gain in energy.
Almost there.
Energy cannot be created or destroyed.
Yes, it can only be transferred from one form to another. So when you drop a stone off a cliff, it's kinetic energy, but once it lands in the water, it's transferred to thermal and sound energy. So it's a bit of a contradiction to say that you're wasting energy, but usually energy is just converted to a form where it's just not ideal for us to use. Maybe it's not the type of energy we want to use. For example, when we are skating, sometimes energy is also lost due to friction, due to thermal energy. But this thermal energy is the kind of energy that we do not want. But it's not exactly waste. It's not exactly wasted, as energy cannot be destroyed. So in a system, your total amount of energy cannot be changed. Fortunately, a lot of these questions actually deal with this kinetic and potential energy. So you can just consider the increase or decrease in energy in these questions. You do not need to be concerned with other values. So, for example, talking about the stone question again, if I throw the stone up or when the stone falls down, it also loses a bit of energy, thermal energy, because you're also working against the air. And once you hit the ground, for example, dropping my pen to the table, it's also wasted as sound energy. Or for example, we have chemical energy, it's really stored in our muscles. But if I sit here all day, it becomes quote unquote wasted energy. In which energy is not destroyed here, but it's just energy that we do not use or isn't ideal. We do not want. So let's try an example. Maybe we can start with Yinzi this time. 50 joules of work must be done to lift a vase from the ground up to a shelf. So when the vase is on the shelf, what is the gravitational potential energy? Talk about the conservation of energy. 50 joules, correct. So what if it falls off from the shell, how much kinetic energy does it have just before it hits the ground? Just before.
50 joules.
There we go. So once it hits the ground, it shatters, and we'll be in really deep trouble because we just broke it. But where does this energy go to?
Transfer to sound energy and thermal energy.
Yes, very good. So we have covered the law of conservation of energy already. Okay, I mean, this is a little trick question. The thing is, we've always considered that why not you use energy to spin the generator itself so that it can create energy for the motor, and when the motor produces energy, it can produce energy to continue spinning the generator. Why can't we do this?
Because there is friction.
No, wait, I want Charmaine to answer this one. A trick question.
Hold on.
Try relating back to the laws of conservation of energy.
Because energy cannot be created or destroyed, is it?
Yep, correct. So when the generator produces energy, and
It
it
is
uses it's transferred to the motor and the fan. The thing is that you can't just suddenly create energy to keep the motor spinning. You can't sustain the motor to create energy because it cannot be created. Yeah, which is why factories have to use fossil fuels, because fossil fuels release chemical energy to spin the turbines.
Okay.
So now we get a little more specific. We're going to more of questions including kinetic energy and potential energy. These are the kind of energies that you see very frequently in IGCSE, and usually the only ones where you need to do calculation. So how do we calculate potential energy? So the potential energy right here is equal to work done if the ball falls to the ground. So we need it to be equal to the force times the distance. Be very careful here, because our force here will be equal to our weight. Our weight is not the mass. Our weight is equal to the mass multiplied by the gravitational field strength, which is why it's equal to mg. When it talks about the weight, you will go for mg, which is also equivalent to force in this case. So if you move this vertical distance, h, your gravitational potential energy will be mgh. Now, let's try a question here. Let's say I have a slope, which is 5 meters long. Let's say I have a cube at the bottom. So this cube is 1 Newton. Let's say if no other energy is involved in this equation, if I move this cube to the top here, what is my gravitational potential energy? What would it be?
Uh,
You can
What
refer
is
to this
the height?
diagram. What is it?
What was the height?
Okay, let's say we have a slope here. We have a length of 5 meters here, and we also have a vertical height of h. If I have a cube, a block of weight 1 newtons, when I move it to the top, how much gravitational potential energy does it gain?
1h.
Correct, 1h. So questions might trick you. Sometimes they have slopes and everything, but do not concern yourself with this slope unless you're using your force to move it up the slope. If you're talking about gravitational potential energy, always consider only the vertical height. So it doesn't matter whether you go down like this or so. The most important thing is, what is our distance, our vertical height here? Sorry, not distance. What's our vertical height when it moves down here? So do not be concerned with this distance, this length, this curly line, but only the height. So I understand for your new IGCSE syllabus, you guys need to use 9.81 4G. Am I correct?
Yes, I think.
Yeah,
9.8.
9.8. Yep. Because I actually took the 2022 IGCSE, the final year before the syllabus changed. So it was still 10. So this is an older textbook, so I'll need to do a correction. So please use 9.8 in your workings. So for example, if your 2 kg mass 3 meters above the ground, this one will become 9.8 instead. So please do watch out for this. How about kinetic energy? How do we calculate kinetic energy? I've actually also been a little curious about this. So we know that work done is force times distance moved. So have you guys learned that force is also equal to the product of mass and acceleration from Newton's second law?
Yeah.
Yes.
All right. So we know that mass times acceleration times distance moved will be work done. So our acceleration is our rate of change of velocity. So it's v minus u over t. And our distance moved, because speed is also equal to distance over time, distance is also equal to the speed and the time taken. So notice that time taken can cancel each other out. So we want to know what is kinetic energy. So it's will be equal to the mass times the gain in speed times the average speed. Our average speed is considered half v, let's say, when our gain in speed is something like this. We have 0, we have v right here. This is our velocity, and this is our time. So our average speed will be half v. Which is why it's equal to half mv squared. When I learned kinetic energy back in the days, we didn't even learn why it was half mv squared. We were just given half mv squared. So this is a very good explanation on how to calculate this. So let's try a question on half mv squared. Do be careful when they ask like doubling the speed, because 2 squared becomes 4. So for these questions, just assume that kinetic energy and potential energy are the only types of energy which are acting on this stone. You do not need to concern yourself with other types of energy unless the question states so, like friction or thermal energy. So if, let's take an example, a more interesting example here. So the stone on the right here slides down a smooth slope. What's the speed when it reaches the bottom? We will only take 2 energies into consideration. We have potential energy at the top, and at the bottom, comparatively to the top, we have already lost all our energy here. Potential energy. Just be converted all kinetic energy, assuming no other forces act. Because when they say it's a smooth slope, there's no friction. You do not need to be worried. So let's start. Our gravitational potential energy at the top of the slope will be mgh, so it's equal to 4 times 9.8 preferably times 5. So 9.8 will actually change this value to, let me see, 196 joules. So you can change that to 196. And so, because all your potential energy was converted to kinetic energy, at the bottom of the slope, you don't have any potential energy comparatively anymore. So this becomes 196. So apply your equation, 1 over 2 mv squared to 200 joules, or 196. So you can go half times 4 times v squared. So This is not the way anymore because when it says M, it's equal to the mass. So if it's 4 kg, it's 4 kg, but if it's mg, just go 4 times 9.8. So with our more accurate value here, we should get, let me see, 9.9 meters per second, which is pretty close to this. Even if it falls vertically, we have potential energy and we have kinetic energy in the end. So only be concerned with these two values when you perform workings in your questions, unless stated otherwise. Let's try with Charmaine this time. So in this question, they ask you to assume that G is 10 instead. Let's just assume it's 10 for the moment.
Okay.
Other frictional forces, just make it negligible. So, number 1, an object has a mass of 6 kg. So let's save it. What is your gravitational potential energy? Part 1, if it's 4 meters above the ground. Part A. What will you use?
MGH.
Correct? So, what will be M?
6 kg.
Yep. Oh, let's just wrap this up quickly. 6 kg. Your G will be 10. So what's your 8 for part A? Which is your vertical height. Yep. So what would be your gravitational potential energy for part A?
240
Correct.
joule.
How about part B?
360 joule.
Yep, correct. All right, let's maybe Alvin. Okay, Alvin, try the next one. An object is a mass 6 kg and a speed of 5 meters per second. What's its kinetic energy?
Kinetic energy 1 over 2 mv square means
Okay, could you
M
write
is
your
6.
could you write your working here?
Oh, okay.
It's preferred.
I'm type up.
Okay, no problem. Well, Yinzi, maybe you want to try the third one. So what's the speed of the ball when you have a mass of 0.5 kg and you have 100 joules of kinetic energy? Yinzi, maybe you can work on
Do
the
I
third one. Yeah,
do
on
I
the
need
third
to
question.
change the 0.5 kg to the 9.8?
No, not needed because kinetic energy is 1 over 2 mv squared. So it doesn't concern anything with weight.
I calculate is 75 joules.
75 joules is correct. Half times 6 times 5 squared. How about if your speed is double? Be careful, it is not 150 because v squared. What would it be?
No, 5 in doubles means 10 square. So 10 square would be 300 joule.
Correct. So maybe Alvin and Charmin, you can try working out question 4, which will be pretty much the same. I don't think it's tricky for this, except for part D. I'll ask a question about part D.
Alright.
So let's start with Charmin first. So what's the kinetic energy of the ball if you have a mass of 0.5 kg, if it is about to hit the sea, and you have a speed of 10 meters per second? What's your kinetic energy?
Should I write down the working?
Yeah, sure.
Okay. Hold on.
Well, Yinzi, have you done your workings for question 3? All right, let's
Is
take a
it
look.
like
Yep, 100 joules is equal to half times 0.5 because it's your mass and v squared. So your v squared will be equal to 400, which is 20 meters per second. This is correct. Okay, Yinzi, maybe you want to start working on part B next. What's the ball's gravitational potential energy before it was dropped? So just giving you a hint, is also equal to your kinetic energy, assuming that we don't have other energies right here, because it's about to hit the sea. And after both of you two are working, maybe Alvin can work out from what height was this ball dropped.
Okay.
Yeah, that's not working.
Let's take a look. What hits the ground? So you have a mass of 0.5 kg and you have a speed of 10 meters per second. It is indeed correct, 25 joules. So what would be the potential energy before it was dropped?
calculating?
You do not need to calculate for this question. Calculations for this question are not needed, so long as you use the conservation when your object, 25 joules. But usually you can make a direct inference from this, so long as it doesn't hit the water, so no other energy affects it. So Alvin,
Okay.
from what height was this drop?
5.1 meter.
5.1 meters when okay, for this question just assume G is 10.
Yes. Oh, okay. So, okay, means 5
5 meters,
meter.
correct. What if you have a stone of mass 1 kg? Now, before anyone does any working, could you guys tell me whether what's the height and why is it different or not different? Let's try. What will be the height when you have a stone? This time it is 1 kg. And it falls into the water. And you have this energy right here. So what height was it dropped from?
Half of
10
the
meters.
original height.
The answer would actually be still 5 meters. Now, I know this sounds confusing. Wait, if it's heavier, shouldn't it be dropped higher? Shouldn't it be dropped lower? Or things like this. But let's analyze our equation again. Pardon me if my drawing skills are still pretty subpar. So 1 over 2 mv squared is equivalent to mgh. This is what we get for kinetic energy and potential energy conversion. Once we cross this out, we see that mass has nothing to do with the equation. No matter how heavy or how light your object is, the height that it falls is dependent on your speed and, of course, our planet's gravitational field strength too. So we can actually make a conclusion here that v squared is equal to 2ga. So your height is equivalent to v squared over 2g. Which means that the only things that affect it are the speed and also the gravitational field strength or your gravitational constant. Please bear in mind if you go to another planet like Mars, it is no longer 10 newtons per kg. It changes to something like 3 point something. For the moon, it's about 1.67. So be wary. Usually you use this if the planet is Earth. So I shall stop this meeting for the moment. We will get back in a while. Let's say 3:30, where I'll be covering the next section 4.04, 4.05, and see how far we can go. So I'll see you in a while. Just take some time, drink water, go to the toilet if you need to, and I'll see you all in a while.
Okay.
Okay.